The artificial intelligence industry is currently expanding at a rate never seen in the history of business. Major AI labs are now adding the equivalent of an entire decade's worth of traditional software revenue in a single month. But that hypergrowth has hit a physical wall. The primary bottleneck for AI is no longer the acquisition of silicon chips, it's the search for the raw electrical power required to run them. Existing electrical grids are effectively tapped out. Across the world, these substations and transmission lines face years-long delays for upgrades and zoning approvals, making it nearly impossible to keep pace with the power demands of new data centers. Because the lead times for grid expansion often exceed the 3 to 4 year useful life of the AI chips themselves, the industry is hitting a timing mismatch that the surface-level grid cannot solve. To keep scaling, the search for power has to move beyond the terrestrial grid entirely. This is what a modern terrestrial data center looks like. It consists of massive server racks, packed shoulder to shoulder in tightly confined aisles. Down here, linking these machines requires thick, heavy copper cabling. To minimize signal delays and power loss, engineers are forced to squeeze these racks as close together as possible, creating intense clusters of heat and noise. Overcoming these constraints of heavy wiring, massive heat generation, and grid dependency requires an entirely different environment. The hardware has to go to orbit. Launching computers into space solves these problems by inverting Earth's physical bottlenecks, turning the most difficult aspects of terrestrial engineering into automated advantages. When we hear about data centers in space, the mind often goes to science fiction, massive, solid buildings floating among the stars. We tend to imagine a structure with a footprint like the Pentagon drifting through orbit. But launching a single monolithic object of that size would be physically and economically impossible. The real architecture is decentralized. It relies on a network of individual AI server racks, units that weigh roughly 3,000 pounds and are about the size of a standard server rack on Earth. The immediate challenge is power. A single top-tier AI rack demands about 100 kilowatts of continuous electricity, and in orbit, there is no utility company to plug into. A sun-synchronous orbit provides the solution. By locking the flight path at an angle relative to the sun, the machine stays permanently illuminated, bathed in sunlight. With constant exposure, the central rack deploys 500-foot solar wings, harvesting an uninterrupted stream of energy. By isolating each unit and manipulating its orbit, engineers can bypass the terrestrial energy shortage with an infinite, reliable supply of solar power. The second major hurdle is thermal waste. Pumping 100 kilowatts of power through a single hardware rack produces enough heat to destroy the electronics. To keep servers from melting, the system uses hundreds of feet of trailing radiators, venting that extreme heat into the freezing void of deep space. Next is the networking. On the surface, distance requires heavy copper to maintain speed. But in space, while launch weight is limited, physical size and the distance between floating units no longer impose a penalty. Instead of physical cables, these server racks connect by firing lasers at each other across the void. Because space is a vacuum, there is no atmosphere to scatter the light. These lasers travel unimpeded, allowing racks to communicate and share data instantly across vast distances. The freezing temperatures and empty vacuum of space may be hostile to life, but for high-performance hardware, they transform Earth's greatest physical constraints into structural advantages. Scaling this means stitching thousands of these independent, solar-powered units together using that laser grid. This constellation creates a virtual data center wrapping the globe. It functions as a single, highly distributed supercomputer, but one that exists entirely outside of any national power grid. We know the networking physics work because companies like SpaceX already utilize this exact laser-through-vacuum technology to route data across the Starlink satellite fleet today. Scaling these systems into a global compute network is the direct evolution of hardware already operating successfully above the atmosphere. There are still near-term practical limits. The sheer volume of continuous, concentrated processing required to train a new AI model will likely keep that phase of development grounded in terrestrial data centers for now. But inference, the day-to-day work of answering user prompts and running queries, is highly distributable. This makes it the ideal workload for a vast orbital network. The appetite for AI compute is boundless, and our surface-level infrastructure is no longer capable of keeping pace with the scale of the demand. Orbital compute is the physics-driven response to those terrestrial limits. It ensures the next era of technological growth isn't derailed by the scarcity of power here on Earth.